Business process monitoring is becoming prevalent through the development of new business process management infrastructures and monitoring tools. Often process simulation and optimization is performed offline and decoupled from the running process. The offline simulation, although based on real collected data, is often outdated and doesn't reflect the running system. This CAS project brings together academic researchers from York University and software architects from the IBM Toronto lab to investigate the automatic building of a simulation model used for business process optimization. We propose a state estimator with a particle filter to keep the simulation model in sync with the running system in real time. The proposed state estimator was developed and integrated with WebSphere Business Monitor and WebSphere Business Modeler as a proof of concept. Using simulation to evaluate a process against a set of metrics is often much more cost-effective, safer, and more flexible than experimenting on the real system. Jay Bennion, who was a manager and lead for process simulation in WebSphere Business Modeler, pointed out that process simulation tools needed to have the ability to run simulations dynamically, allowing the user to conduct what-if scenario analysis. Furthermore, he stressed that forecasting of monitored KPIs needs to take process load and structure into account, instead of doing extrapolation solely on the KPIs themselves. Realizing that an accurate simulation model that reflects the running process is vital to achieving the requirements outlined by Jay, our research challenge then becomes how do we utilize monitored data of the in-flight process to update the simulation model. Monitored values, for example task duration, cannot be fed back as is into the simulation model since it contains parameters that aren't explicitly modeled by the simulator. For example, we can see here that the task duration measured by monitor contains both the actual task duration and noise such as queuing delays and overhead. Take for another example, consider the process shown here, where D1, D2, and D3 refers to duration of each of the respective tasks. Now, if we measure the end-to-end duration, shown here in blue, we notice that it does not equate to the sum of the individual task duration, shown here in red. And the reason is that there are hidden parameters such as link duration and network latency. Here we see the conceptual architecture of our proposed system. Notice that the monitored data is fed through a particle filter before reaching the simulation model. Particle filter is the component responsible for removing the queuing and overhead noise from within the tasks themselves. To test the effectiveness of our state estimator, we conducted experiments where we compared end-to-end process duration produced by a simulation model updated using a particle filter with that from a simulation model updated using values directly from monitor. Here in the graph below, the blue line represents the monitored KPI. The green line is the KPI given by the simulation model updated using a particle filter. Notice how the green line practically overlaps the blue line. Conversely, the purple line is the KPI given by the simulation model by blindly feeding in values directly from monitor without the use of a particle filter. Notice that the KPIs measured does not match the actual monitored data. We will now take a look at a usage scenario of a prototype with respect to our conceptual architecture. First, a business process is created and modeled in a process modeling tool, such as WebSphere Business Modeler. Next, the user is able to trigger process simulation and at the same time specify that they would like to use monitor data as input to the simulation engine. This figure shown here is actually a screen cap of our prototype. In addition to conducting simulation using real-time monitor data, the user also have the option to pull historic values from the monitor server by specifying a start and end date. Then by clicking Next, monitor data, be it real-time or historic, is pulled from the monitor server and fed through particle filter, eventually into the simulation model. The technology developed in this CAST project is applicable to any process modeling tool where processes can be simulated against a set of metrics, where the simulation parameters are entered at modeling time and remains static until explicitly updated, and where KPIs can be forecasted. An example of such a process modeling tool is IBM's WebSphere Business Modeler. With our proposed state estimator, we're able to tune a process simulation model such that it reflects closely the running process. This allows the user to conduct what-if scenario analysis on an accurate simulation model. It also improves the predictive capabilities on KPIs by taking into account current load and process structure. To further encourage adoption of our technique by IBM products, we could extend our techniques in the following way. We can provide better trend predictions based on regression techniques. We can optimize business goals by tuning or reallocating resources or changing business rules based on simulation results. And we can suggest to the user a set of process modifications that will help minimize or maximize a certain KPI.